welcome to the deep dive. Today we're taking a really deep look into something that's fundamentally changing how you as a game developer approach creating those really vibrant, immersive, natural environments. We're talking about foliage using Unreal Engine's incredible Nanite virtualized geometry system.
That's right. Yeah, we've pored over, well, basically everything we could find. The latest insights, research, practical experiences from the community and, from Epic Games themselves. Our sources cover everything from the huge shifts in modeling and art direction that Nanite really demands, right through to the, let's say, complex challenges of bringing these assets to life with realistic wind animation.
Yeah, and our mission today is to sort of cut through all the noise and just give you the essential knowledge you really need. We want to guide you through what Nanite means specifically for foliage, why it's such a massive departure from the techniques we've all been using for, well, decades, and how the common animation methods, world position offset, skeletal rigging, even things like vertex animation textures, how they stack up in this new world.
Think of this as your shortcut, your essential briefing to get you up to speed on Nanite Foliage. The critical details, the potential, pitfalls to watch out for, and the really exciting opportunities for visual fidelity it unlocks.
Let's dive in.
Okay, so at its core, Nanite, it really represents a true paradigm shift. It's a fundamental change in how real-time graphics handles geometric complexity. It's not just about rendering, slightly higher polygon counts. It's an entirely new architecture, built from the ground up, built to manage detail right down to the pixel level and handle massive numbers of objects, things that were just impossible before within real-time budgets anyway.
Right. For so long, every artist, myself included, has been locked in this constant battle with the polygon budget. Every tree, every rock, and especially dense stuff like bushes and grass. It felt like a constant negotiation, just desperately trying to shave off triangles here and there.
Exactly. And Nanite's fundamental power, the real magic, lies in its ability to intelligently process and render only the geometric detail that you, the viewer, can actually perceive at any given moment. And that's regardless of how many polygons are actually in the source mesh.
Okay, so that's different from traditional LODs, right?
Right.
Level of detail systems.
Totally different. A crucial departure. With old LODs, you created multiple separate versions of the same mesh. You'd have your high poly for close-up, maybe a medium poly for mid-distance, and then a low poly one. Sometimes it's just a super simplified shape or even an imposter billboard for far away. And the engine would just swap between these entirely different meshes based on distance.
Yeah, and that's where you get those horrible, jarring LED pops, a tree suddenly visibly changing its shape or outline as you got closer or moved further away.
Exactly. The absolute bane of environment artists everywhere. Nanite avoids this completely. It works on a much, much finer granularity. It doesn't swap entire messes like that. Instead, it uses this highly compressed internal mesh format and a really sophisticated fine-grained data streaming system. It looks at the full resolution source mesh, the original high poly one, and figures out which specific triangles or clusters of triangles are actually needed to maintain visual fidelity at the current pixel resolution. Then it streams and renders just those necessary pieces.
Whoa. Okay, so it's not about swapping between, say, 3 pre-made versions. It's dynamically selecting exactly the specific triangles needed based on what you can actually see right now, even down to tiny details only visible up close.
That's pretty much it. And because this selection and streaming is dynamic and it's based on screen space visibility, it gives you automatic, completely seamless LOD transitions. You get rid of those LOD pops entirely because the geometry is being simplified and refined continuously, not just swapped out in big chunks.
That makes sense.
And historically, like you said, real-time foliage has been one of the biggest performance bottlenecks, just because it involves incredibly high polygon counts, potentially spread across thousands or even millions of individual instances. The cost just adds up massively.
Oh, I know that pain. Placing a forest and watching your frame rate just tank.
Absolutely. Nanite's architecture was specifically designed to tackle exactly these kinds of problems, really dense, complex geometry, and massive object counts. So its impact for foliage is, well, profound. It truly unlocks the potential for unprecedented geometric fidelity. It lets artists finally move away from techniques that were, frankly, necessary workarounds born purely out of polygon limitations.
Like those 2D alpha cards we always use.
Exactly, the heavy reliance on 2D alpha masked cards. Now artists can move to methods that can actually embrace the inherent complexity of natural forms using true 3D geometry. It fundamentally changes how we even think about building foliage assets.
Imagine the freedom. Not having to spend agonizing hours manually creating and tweaking those separate LOD levels for every single bush, or desperately trying to optimize every loose polygon count. That whole geometric burden is, like, significantly lifted.
Which brings us right to the most significant immediate consequence of nanite for foliage artists. And that's the strong push, and frankly the practical necessity, to transition away from those long-standing 2D alpha-masked cards and really embrace fully 3D geometry instead.
But 2D cards have been the standard for so long. They were the go-to solution for handling high poly leaves and branches efficiently. Why is nanite pushing us away from something so established?
Well, the main drivers are twofold, and they're pretty compelling when you dig in. First, there are significant performance advantages, but specifically in a nanite context. And second, there's just a dramatic leap in visual fidelity.
Yeah.
Let's start with performance, because honestly, it's kind of counterintuitive for a lot of people.
It really is. My first thought is, okay, a full 3D model, even with nanite helping, must be heavier computationally than a simple flat card. Right.
And that's the critical misunderstanding, based on how we used to think. Empirical evidence and the official documentation from Epic Games strongly suggest that nanite prefers and is actually most efficient with real 3D geometry, especially when that geometry uses opaque materials. Now, here's the crucial point that often trips people up. Just enabling nanite on your existing library of traditional 2D card-based assets that rely heavily on alpha masks, might not actually improve your performance. In fact, in some cases, it can even be slower than rendering those cards the traditional non-nanite way.
Okay, wait. That makes absolutely no sense on the surface. How could a nanite-enabled asset perform worse than its non-nanite version sometimes?
It really comes down to how nanite and the rendering pipeline handle masked materials and critically overdraw. Masked materials, by definition, have large areas of transparency defined by the alpha channel, right? The leaf shape is there, but it's on a larger transparent plane. Even though you can't see those transparent parts, the engine still has to do work related to them. With traditional methods, you'd use various alpha testing or blending techniques, but with nanite, even the masked out pixels, the completely transparent parts of that large card plane, can still incur a significant processing cost. It's almost as much cost as the pixels that are actually drawn.
Wow. So the cost isn't just in drawing the visible leaf shape itself, it's in processing the entire card plane and figuring out which parts are masked away.
Essentially, yeah. Nanite's real strengths lie in efficiently culling and simplifying solid geometry. When you give it a large plane with an alpha mask on it, you're basically presenting it with a lot of empty space that it still has to factor into its processing and culling decisions. The true performance benefit for foliage with nanite is realized when you make that transition to models composed of solid 3D geometry. This allows nanite to be much more efficient with its rendering and culling because it's dealing with tangible volumetric forms without those large areas of expensive transparency. You're feeding nanite the type of data it's best optimized to handle.
Okay, that clicks now. You need to lean into nanite's strengths.
Yeah.
Solid geometry and ideally opaque materials. So, better performance potential if you use the right approach. What about the visual side of things?
This is where the advantages are just immediately and dramatically apparent. Moving to fully 3D forms fundamentally eliminates that flat, often papery look that's so common with card-based assets. You know that look from certain angles. You can clearly see the razor-thin edge of the card sticking out, or you see two flat planes intersecting in a really unconvincing way.
Yeah, it totally breaks the illusion. It looks like a paper cutout someone just tacked onto a branch, not like a real leaf with actual substance.
Exactly. So, with true 3D geometry, you get immediate, tangible benefits. Leaves have actual thickness and curvature. Branches feel like they occupy real space. This allows for accurate self-shadowing within the foliage asset itself. A leaf can cast a tiny shadow on another part of the same leaf or on the stem right below it. These 3D forms interact much more naturally and, well, nuancedly with dynamic lighting sources. There's a tangible volumetric presence in the world that you simply cannot achieve with flat cards.
That heightened realism must contribute hugely to immersion, right?
It really does. It makes the foliage feel properly integrated into the 3D world, not just sort of layered on top like decals. And as kind of bonus visual advantage, this shift towards 3D forms naturally makes it easier to use opaque materials for many parts of the foliage, which, as we just discussed, are generally less performance intensive with nanite than masked ones. So you get better potential performance and a significant visual fidelity upgrade. But yeah, it demands a fundamental change in how we actually build the assets. And it's also important to acknowledge that while nanite itself is pretty robust technology now, its application specifically to foliage is still relatively recent compared to, say, using it on solid architectural meshes or big rocks. Features like nanite displacement or hardware accelerated tessellation using nanite were still noted as experimental as recently as Unreal Engine 5.3.
Okay, so it's not like a decade-old, completely ironed-out workflow. The best practices we talk about today are still somewhat in flux.
Oh, precisely. The core nanite system is stable, absolutely. But the specific optimizations and the ideal workflows for dealing with the unique challenges of foliage, which often falls under the category of aggregate geometry or maybe sparse geometry, meaning lots of fine disconnected pieces like individual leaves or needles or grass blades, those are still maturing. This means that the best practices we're discussing today represent the current leading edge of understanding within the industry and, at Epic Games. Workflows will undoubtedly see ongoing refinements, new engine features will definitely be added, and there might be adjustments as the technology continues to evolve.
So for you, the developer listening in, maybe while you're working on something else, getting familiar with this now, even while it's still evolving, kind of puts you ahead of the curve. You're jumping in early on something that's only going to become more central.
Absolutely. Early familiarization is a significant advantage because both nanite and its related systems, like Lumen for dynamic global illumination and reflections, will continue to see major development. Maintaining an adaptable approach and really a commitment to continuous learning is essential to truly maximizing the potential of nanite foliage in your projects down the line.
All right, let's just take a brief pause here. Quick recap. So far, we've established nanite's core power for handling geometry at basically unprecedented levels. We've talked about why moving to full 3D geometry is really the key for both performance and visual fidelity compared to the old 2D cards, which is maybe counterintuitive at first. And we've noted that this whole area of nanite for foliage is still a relatively new and evolving part of the engine. Things will change.
Yep. Exactly. And building on that foundation, this technological shift also has a really profound impact on the artistic side of development, on art direction, and just the daily work of environment artists.
Okay, so if we're no longer strictly limited by polygon count in the same way, how does that change what artists can and maybe should be focusing on?
Well, nanite genuinely liberates artists from those super tight polygon budgets that constrain traditional foliage creation for so long. And this freedom presents an incredible opportunity to incorporate geometric details that were previously just unfeasible in real-time rendering.
Like you mentioned adding thickness to every single leaf before. Is that really practical now?
It really is. Individual leaves can now have meaningful thickness, natural curvature, and detailed edges. Branch structures can be modeled with intricate twists, turns, and natural imperfections. Subtle details like small tears in a leaf edge, or maybe insect damage, or the raised texture of veins. These can now be represented with actual geometry, not just faked with normal maps or alpha textures.
And how does that level of detail actually impact the final look in-game?
It has a really profound impact, actually. It significantly enhances the silhouette of the foliage, making it feel more substantial and unique from different angles. It enriches the interplay of light and shadow because you have real 3D forms casting tiny self-shadows and catching highlights in complex ways. And perhaps most importantly, it provides incredibly compelling close-up views that truly hold up to scrutiny. Imagine seeing like a single hero leaf in the foreground, catching the sunlight, casting those tiny self-shadows on its own surface, maybe with a slightly torn edge that's defined by actual geometry rather than just a blurry alpha mask. It's a huge difference.
Okay, that sounds amazing for pushing realism. But it also sounds like a potential trap. If artists can just add infinite detail, won't they just go overboard and create assets that are, pointlessly dense?
And that's the crucial artistic consideration right there. This newfound power absolutely demands artistic judgment. While nanite can handle vast amounts of detail, not all detail is equally impactful or necessary for the final result. The principle of purposeful polygons is still highly relevant, maybe even more so. Any detail you add should really serve the overall aesthetic goal, whether that's realism, stylization, or something in between, and contribute meaningfully to the believability, the visual interest, or the specific style you're aiming for.
So don't just sculpt micro-wrinkles everywhere if they won't even be visible at typical gameplay distances, or if they don't actually add anything to the overall form or silhouette.
Exactly. Just blindly increasing poly count without clear artistic direction can easily lead to visual noise, cluttered-looking assets, or even computational inefficiency, believe it or not, even for nanite. Good practice, even with nanite, is to maintain a degree of artistic optimization. Make sure the geometry you're adding meaningfully contributes to the final visual experience. The focus shifts dramatically. It's no longer about minimizing polygons at all costs, but about using the, let's say, generous budget intelligently and purposefully to achieve your desired artistic vision.
And this massive leap in fidelity for foliage. It must raise expectations for the rest of the environment, surely.
Oh, it absolutely does. This shift towards incredibly detailed, volumetric foliage inherently raises the baseline quality expectation for all the environment assets in your scene. If your trees and bushes look incredibly realistic and hold up perfectly in close-up, then elements like your rocks, your terrain details, maybe nearby props, they might also need a similar uplift in fidelity and geometric detail to maintain visual harmony and consistency across the entire environment. Your art director will likely expect more detail overall, but you still need to be smart and artistic about where you actually add that detail. Don't just go crazy with ZBrush subdivisions everywhere without thinking.
Okay, so nanite enables much higher detail, but it requires really smart artistic choices about where to put that detail. Does it force you into like a hyper-realistic art style? Or can you use it for other looks?
Not at all. Nanite is remarkably versatile. It supports a really wide spectrum of art directions, from extreme hyperrealism all the way to highly stylized looks. For realism, yeah, obviously it allows artists to replicate complex botanical structures and micro details found in nature with unprecedented accuracy. High-quality scanned assets like detailed tree trunks or maybe larger plant structures from sources like megascans, they integrate much more readily because nanite is built to handle their inherent geometric complexity right out of the box.
And what about for stylized art? How does it help there?
Well, for stylized directions, nanite enables you to create foliage with, say, chunky, graphic, or really well-defined geometric forms that truly hold their intended shape and volume from all viewing angles. This directly avoids that flat or decal-like appearance that can sometimes affect stylized foliage built using the traditional card-based methods.
That makes a lot of sense. A stylized leaf that's actually modeled as a solid, maybe bevel shape will look solid from every angle, whereas a stylized leaf painted on a flat card might just look like a sticker depending on how you view it.
Precisely. And the core principles of good foliage art direction, understanding natural branching patterns, creating believable density and clumping, focusing on strong silhouettes, those are still absolutely fundamental regardless of the style or the technology you're using. The key takeaway here is that nanite provides a more robust geometric foundation upon which you can build any artistic choice you make, whether it's realism or heavy stylization.
This whole transition from relying on 2D cards and alpha masks to really building and thinking in pure 3D geometry, it sounds like it demands a pretty significant adjustment for artists who've been doing it the old way for years.
It absolutely does. Yeah, it requires a significant mindset shift. The old habit was basically faking volume and form by carefully arranging intersecting alpha cards. You were essentially painting with flat planes and transparency to suggest depth. The new mindset requires you to think, model, and sculpt in true three-dimensional space right from the outset.
So a much stronger emphasis on foundational 3D art skills is needed, like organic modeling.
Precisely. There's definitely a greater emphasis now on fundamental organic modeling skills, sculpting abilities, and having a solid understanding of botanical structures, how plants actually grow and form. The primary definition of shape, form, and volume now comes directly from the geometry itself, rather than being heavily reliant on the texture's alpha channel and careful placement of flat planes. There's a potential risk here, though, of what we might call geometric noise, or maybe creating visually chaotic foliage if that newfound freedom to add detail isn't managed with a clear artistic vision and good form principles.
And maintaining consistency across different assets seems even more important.
Yeah, maintaining a consistent level of geometric detail and artistic execution across all your foliage assets, and really across all your environment assets, is vital for a cohesive and believable visual experience. You have to consciously unlearn those old habits, like relying on alpha opacity to define fine edges or create complex shapes. Instead, you need to look for geometric solutions wherever it's feasible. Now, as we touched on earlier, one specific nanite challenge that is particularly relevant to foliage is how it handles what's called aggregate geometry. This basically refers to meshes that are made up of many small, relatively disconnected parts. Think individual leaves, grass blades, pine needles, tiny twigs. This type of geometry is inherently less efficient for nanite's occlusion culling and its simplification algorithms compared to solid, contiguous objects like, say, a wall or a large rock.
Okay, why is that exactly? Why is it less efficient for nanite?
Well, because nanite works best when it can simplify amplify and cull large chunks of solid surface area that are hidden from view. With many tiny separate pieces, there's just less contiguous surface for it to work with efficiently. It has to manage the bounding boxes and visibility calculations for all of those individual tiny elements. This means that even with Nanite's incredible power, art direction must still carefully consider foliage density and the potential for multiple layers of geometry drawing on top of each other, because very dense arrangements of highly detailed geometric foliage can still pose performance challenges, especially if they're composed of millions of tiny separate meshes.
Right. But despite those specific challenges with aggregate geometry, the overall visual payoff is huge. You mentioned the end of papery foliage earlier, and that sounds like a game changer.
Yeah, this is arguably the single most significant visual win for nanite foliage. You get an authentic representation of volume. Leaves and branches have tangible thickness. They actually occupy space in a way that flat 2D cards fundamentally cannot. This enhanced volume creates a much greater sense of depth, richness, and sheer believability in your environments.
And it must get rid of those really obvious visual artifacts we used to see all the time with cards.
Yes, it largely eliminates those telltale signs of traditional card-based foliage, seeing those paper-thin edges sticking out at weird angles, or seeing obvious unnatural intersections between flat planes where they cross each other. Light interacts much more naturally with these volumetric forms, creating softer, more believable self-shadows and highlights within the foliage itself. The end result is foliage that integrates seamlessly and convincingly into the 3D world, significantly boosting the player's sense of immersion. It just feels more real.
All right, okay, so just to sort of bring together everything we've said about the art direction and artistic side of things, the new Nanite workflow means you really need to embrace geometric detail, but do it smartly. Balance realism or stylization while actively breaking those old 2D card habits and strengthening your core 3D modeling skills. The immense payoff is truly volumetric foliage that feels like a real part of the world, finally getting rid of that papery look. But you still need to be mindful of challenges like Nanite's handling of aggregate geometry and managing density carefully. So the key artistic principles here are using purposeful polygons, strengthening your 3D modeling fundamentals, maintaining a consistent detail level across all your assets, understanding the aggregate geometry challenge, and aiming for that transformative volumetric presence.
Yeah, those are excellent points to keep in mind as you approach this. Now that we've covered the fundamental shift and the artistic impact, let's get really practical. If we're moving to 3D geometry, what are the core modeling strategies and workflows you should actually adopt, both for maybe converting old assets and for creating new ones from scratch?
Okay, let's start with converting existing 2D assets. I imagine many studios have massive libraries of traditional foliage built up over years. Is it even feasible or worth trying to convert those?
It can definitely be a pragmatic and sometimes necessary starting point, yeah. Especially for studios with extensive libraries of production-ready 2D card assets. It might not always achieve the absolute highest fidelity possible compared to building brand new 3D assets optimized for Nanite right from scratch. But it can significantly accelerate the adoption of Nanite foliage workflows by letting you leverage that existing work.
How do you even know if a legacy 2D asset is a good candidate for conversion? What should you look for?
Success hinges really heavily on the quality of the source textures, specifically the alpha channel in those textures. You need clear, well-defined shapes for the leaves or the petals or the branches within that alpha map. You have to analyze the texture atlas carefully to identify individual elements that are distinct enough to be logically separated and then given three-dimensional form. If the alphas are blurry or they have really noisy edges, or maybe multiple elements are merged together unclearly in the texture, conversion is going to be much more challenging and might not yield very good results.
Okay, assuming the alpha quality is decent, how do you actually generate 3D geometry from a flat card texture?
Yeah.
What are the techniques?
There are several established techniques in various digital content creation, or DCC, packages. In Blender, for example, a common approach involves using the alpha texture to displace a flat plane. That essentially cuts out the shape as geometry based on the alpha. You would then likely add something like a subdivision surface modifier, maybe 2 iterations, to smooth out the jagged edges from the alpha and add some nice beveling. A typical workflow might involve selecting the mesh areas corresponding to leaves using material IDs, separating those pieces, applying subdivision, adding thickness using an extrude or maybe a solidify modifier, and then potentially merging them back onto a branch structure if needed. Another method in Blender could be tracing the image outline using features like grease pencil and converting that trace into a mesh, though that often requires quite a bit of manual cleanup afterwards.
What about sculpting tools? Can someone like ZBrush help here?
Oh yeah, ZBrush offers a really powerful feature called Make 3D. You can feed it a grayscale alpha map, basically a height map representation of your leaf or shape, and it can quickly generate a base 3D mesh directly from that texture information. This is particularly useful for rapidly generating starting base meshes for many different leaf shapes defined within a single atlas texture. It gives you a great starting point for further sculpting or refinement. Other DCCs, like Maya and 3ds Max, have similar principles you can use. Displacement mapping on planes, extruding faces based on texture selections or vertex colors derived from the alpha, or simply using the 2D card image as a visual blueprint to manually model the 3D shape underneath it.
Okay, so once you have this initial, maybe somewhat rough 3D mesh generated from an old card, what's the next step? Is it ready to go?
No, definitely not. Refining that converted geometry is absolutely necessary before it's really production ready. Even though Nanite is remarkably tolerant of mesh density and topology, cleaner, well-structured geometry is always easier to work with for the subsequent steps like UV mapping, vertex painting, or adding further sculptural details. You'll typically need to perform some level of topology cleanup, and the mesh generated from displacement is often completely flat, so you must add thickness to give it that essential volumetric presence we talked about. Edges that were sharp in the original alpha map can translate to unnaturally razor-sharp edges in 3D, so you'll probably need to bevel, smooth, or even sculpt those edges a bit for a more natural, organic look. And then you'll need to handle the UVs. Ideally, you might be able to preserve the original UV layout from the card for texturing, which is great, but you'll likely need to make adjustments or reproject the UVs after adding thickness or making significant topological changes. The cleanliness of the original UV layout on the 2D card significantly impacts how much UV rework is needed later.
Okay, so converting is one path. It's pragmatic, lets you leverage existing assets, but creating new 3D foliage assets total from scratch. That sounds like the ideal way to really fully embrace Nanite's power, right? What's the workflow there?
Yeah, starting fresh definitely allows you to build assets specifically optimized for Nanite's strengths right from the beginning and achieve the highest possible fidelity.
So what are the best practices for actually modeling these high poly foliage elements specifically for Nanite?
Well, the recommendation is generally to model individual elements, leaves, petals, needles, small branches, thorns, whatever the plant has, as distinct geometric pieces. This gives you the maximum control over their individual shape, how they layer together, how they interact, and allows you to add detail precisely where it's most impactful. The focus really shifts to accurately capturing the realistic or perhaps intentionally stylized thickness, curvature, vein structure, and overall edge flow of these elements. For instance, creating a detailed leaf in Blender might involve starting with a simple plane, adding some edge loops, maybe using the Bridge Edge Loops tool to connect a front and back face to give it thickness, stitching vertices together to control the tip shape nicely, and using techniques like insetting faces to prepare specific areas for subdivision and later sculpting. For elements like leaves, using tools like Z-Spheres and ZBrush to create an underlying skeletal structure first can be really helpful. It helps ensure consistent profiles and natural curvature before you even start adding the surface details.
And sculpting seems absolutely essential for getting those fine organic details right.
It is absolutely invaluable, yeah. Sculpting software like ZBrush is where you'll add all those fine organic details that really make foliage look convincing. For leaf surfaces, you'd sculpt details like vein patterns, subtle surface textures, and natural imperfections like slight folds, twists, or maybe even insect damage. A common ZBrush workflow for a leaf might involve starting with a low-poly base mesh and using features like dynamic subdivision to preview the smooth results while you sculpt. Then maybe using Z-spheres to quickly block out the main and branching vein structures. And then finally using various brushes to add the finer surface details on top. For things like bark on branches or stems, you'd sculpt the bark textures, knots, growth patterns, and any irregularities directly onto the mesh surface.
Now, we keep hearing this phrase that Nanite handles orders of magnitude more triangles. Does that really mean poly count truly doesn't matter anymore? Can we just go nuts?
No, not exactly. Poly count is not entirely irrelevant, even with Nanite. While Nanite absolutely allows for significantly higher polygon counts compared to traditional pipelines, you can definitely create and use much more detailed models than ever before. The key principle still remains purposeful polygons. The polygons you add must still have a clear artistic or functional purpose. You shouldn't just add detail that won't be perceivable at typical viewing distances, or doesn't actually contribute meaningfully to the silhouette, the surface quality, or the overall form.
Right, so avoid adding millions of tiny bumps if they just average out into looking like a flat surface from where the player usually sees it.
Exactly that. And the required poly count per asset also varies hugely depending on the asset scale and its importance in the scene. A hero tree, maybe one intended for prominent close-ups in cutscenes or gameplay, might realistically be 1 or even 2 million triangles, a figure that was previously just unthinkable for real time. But for general game foliage, while the budget per asset is much higher than before, more moderate poly counts are still advisable compared to just pushing unlimited detail everywhere, especially when you consider Nanite's behavior with aggregate geometry, which we keep coming back to. Any mention you might see of 10K per asset in older tutorials or forum posts is likely referring to a different era entirely. The key thing with Nanite is the dramatic increase in the available geometric budget, not that it's suddenly infinite for every single asset. And here's an absolutely critical technical detail for high poly meshes with Nanite. You must ensure your normals are smooth. Heavily faceted, dense meshes significantly increase Nanite's rendering cost on its data size. They really hurt its ability to simplify and compress the data effectively. Click check. If you look at a very dense mesh in your DCC and the vertex count is nearly equal to the triangle count, like a vertex to triangle ratio, Kirchen 1.1 or even higher, that often indicates excessive faceting or maybe issues with imported normals that will significantly hurt Nanite performance. You need to ensure your normals are smooth properly and well behaved.
Okay, makes sense. Even with full 3D geometry, those dense leaf clusters must still create a lot of overdraw, right? Where leaves are drawn on top of leaves.
They absolutely do, yeah. Dense clusters of leaves or branches, especially when viewed from certain angles, still create significant overdraw where multiple layers of geometry are being rendered for the same pixel on screen. Nanite's culling is generally less effective at completely eliminating this kind of internal overdraw within a single complex asset composed of many thin layers. So you need to model your leaf or branch clusters intelligently to minimize unnecessary internal overlap artistically without sacrificing a natural bushy look. Traditional card placement involved careful manual arrangement to avoid obvious intersections between flat planes. With 3D, the concern shifts more towards managing the density of overlapping surfaces within a single complex asset.
A modular approach seems like it would be perfect for managing that complexity and creating variety efficiently.
Yeah, a modular approach is indeed highly effective, and it pairs perfectly with Nanite's strengths. The idea is you create a library of high-quality individual 3D components, maybe different leaf shapes, petals, twigs, thorns, berries, sections of bark, etc. These components are modeled and textured individually to a high standard. Then you assemble these components into larger, more complex plant assets. You can do this manually in your DCC, which gives you precise control, or much more efficiently for things like trees, you can do it procedurally using tools like SpeedTree. SpeedTree excels at distributing and arranging these pre-made components onto a branch or chunk structure according to botanical rules.
And Nanite works well with this kind of component-based approach. No issues with lots of small meshes.
Yes. Nanite's ability to efficiently handle many, many instances of detailed meshes makes this modular strategy particularly powerful. You can have potentially thousands of instances of your highly detailed leaf mesh placed procedurally by SpeedTree, and Nanite handles the rendering of all those instances efficiently. And this is where that crucial Nanite setting for foliage, preserve area, becomes really important again. It's vital when dealing with modular, component-based foliage, especially aggregate geometry like trees with lots and lots of separate leaves. Without it, as Nanite simplifies the geometry at distance and starts removing individual leaf components, the whole plant can visually thin out and look sparse. Preserve area combats this by slightly dilating the open boundary edges of the remaining simplified geometry, basically puffing them out a tiny bit, helping to maintain the perceived density and visual mass of the foliage at distance. And modeling your leaf clusters or components with some degree of natural clumping or slight overlap also helps here. It encourages Nanite to treat them as larger units before it starts aggressively simplifying, which complements what preserve area does.
Okay, let's take another moment just to summarize this whole modeling journey, because that was a lot. We've covered the possibility of pragmatic conversion from old 2D cards, but ideally, you're creating new 3D assets from scratch. That involves modeling individual, detailed components, sculpting organic details, deciding if retopology is needed, often not strictly, but sometimes helpful, focusing on purposeful polygons and absolutely critical smooth normals, managing internal overdraw artistically, and leveraging a modular assembly approach, potentially with procedural tools like SpeedTree, and remembering that crucial preserve area setting in the static mesh editor for maintaining visual density at distance.
Perfect. Now that we've covered creating the actual geometry, the next vital step is texturing and material authoring. Materials are absolutely critical for bringing nanite foliage to life and making it look believable. Many fundamental PBR principles still remain, of course, but there are definitely new considerations introduced specifically by nanite.
First question. Are texture atlases still relevant if we're using fully 3D geometric foliage?
Yes, absolutely. Texture atlases are still highly recommended and widely used, even for meshes made of 3D parts. They are essential for optimizing texture memory usage and reducing the number of draw calls needed for meshes composed of multiple smaller components, like a branch with many leaves. The content of the atlas shifts, though. Instead of holding dozens of alpha masked cutouts of leaves and branches, the atlas now holds the PBR maps, your albedo, normal, roughness, SSS mask, etc., for your individual 3D components, your high detail leaf mesh, your twig mesh, sections of bark, and so on. You lay out the UV shells for these 3D components within the atlas space, grouping similar elements together and ensuring you maintain a consistent texel density across the different parts.
Does Nanite's automatic LOD generation mean we don't need to worry about packing LOD textures into our atlases anymore?
Correct. That's a big workflow simplification. Nanite's automatic geometric LOD generation means you don't need to pack your atlas with textures for multiple pre-baked LOD versions of entire branches or clusters, which was a common practice in older workflows to save texture memory at distance. The focus of your atlas can shift entirely to providing high-quality, unique surface details for the individual 3D parts that will be assembled into your final asset. And a highly useful technique here, as we mentioned briefly in modeling, is baking utility maps like an ID map from your polygroups or material IDs in your DCC and packing that ID map into the atlas alongside your PDR textures. This ID map is extremely useful for easily masking different parts, like separating the leaf blade from the petiole or bark from the underlying wood during the texturing process in software like Substance Painter. It makes life much easier. Okay, now for the material setup itself in Unreal Engine. There's one core principle for nanite foliage that stands out above almost everything else when it comes to performance.
Okay, hit me with it. What's the #1 rule?
Prioritizing opaque blend modes. This is, without a doubt, the single most significant material consideration for nanite foliage performance. Nanite is designed to be most efficient by far when it's rendering solid, opaque surfaces. The guidance from Epic Games is very clear and consistent on this. Nanite will never work better than with opaque shaders. That's pretty much a core tenet you need to internalize. And this preference directly impacts your modeling approach back down the chain. Your foliage assets must be modeled with geometric edges and details to minimize, or ideally entirely eliminate, the need for transparency or alpha masks. Leaf silhouettes, branch tips, everything should be defined by the geometry of the mesh itself, not by an alpha mask in the texture cutting away parts of a larger plane.
So the takeaway is, if at all possible, avoid masked materials entirely for nanite foliage.
Wherever and whenever possible, yes. That should be your default goal.
Okay, let's pause for another quick check-in here. This feels important. We've just walked through the modeling pipelines from converting old cards maybe to ideally building new 3D assets using modular workflows and purposeful polygons. We've emphasized the importance of smooth normals and that crucial preserve area setting for distance viewing. And now we've just hit perhaps the single most critical material point for performance, the huge advantage of using opaque materials with nanite over masked ones.
Excellent summary. Exactly. Now, while opaque is the ideal and the very strong recommendation, you might naturally ask, are there any specific scenarios where you'd still consider using mask materials, even sparingly?
Yeah, are there ever exceptions to that rule, like for really fine details?
There might be, yes. In rare, very specific cases, you might consider using masked materials for extremely fine details that are truly prohibitively expensive or impractical to model geometrically. We're talking about things like the very, very thin tips of exceptionally fine pine needles, or perhaps fine hairs or fuzz on certain types of plants. However, this should be a really carefully weighed decision and used extremely sparingly. Masked materials are inherently more expensive than opaque ones for the renderer, and as we discussed earlier, those masked out, completely transparent pixels still incur a significant rendering cost with Nanite, even though Nanite handles the geometric complexity efficiently.
Okay, so it's basically a performance trade-off you make only for hyperfine detail that you just can't model effectively.
Precisely. And if masked materials are used, it's absolutely critical that the alpha mask itself is as tight as possible to the visible geometry. You want to minimize the area of the transparent plane that the engine still has to process. The trade-off you're making for getting those hyperfine, wispy details becomes: do you try to model incredibly dense, opaque geometry for them, potentially stressing Nanite's aggregate geometry handling limits? Or do you accept the known performance cost of masked materials for those very specific limited elements? The fact that assets like the official Megascans grass pack actually offer both high poly geometric grass and traditional masked cards indicates that this is still an ongoing area of practical consideration and compromise, depending on the exact asset, the target platform's performance, and the visual requirements.
All right, moving on. Materials also obviously need to handle wind and dynamic movement. World Position Offset, or WPO, is the standard material-based technique for this in Unreal Engine. How does WPO interact with Nanite Foliage specifically?
Yeah, WPO is indeed essential for imparting wind animation and other dynamic movements like maybe subtle growth or reactions to external forces. Nanite does support WPO, that's the good news. But its use comes with significant performance implications, particularly on high vertex count meshes like the detailed Nanite Foliage we've been talking about building. The source material we looked at is very explicit on this point. When using World Position Offset, WPO, more vertices equal higher cost. WPO logic must be limited and monitored. Complex WPO calculations that affect every single vertex on a very dense nanite mesh can easily become a major performance bottleneck. Simpler WPO effects are generally much preferable for performance.
And wasn't there a specific setting related to WPO that you mentioned was crucial for Nanite, something about displacement?
Yes, absolutely. There is a critical optimization setting you need to know about: the max world position offset displacement parameter. It's found within the materials details panel in Unreal Engine. What this setting does is it clamps the maximum distance any vertex can be offset from its original position by the WPO calculation in your shader. It is absolutely crucial for nanite performance because it directly helps the engine manage the bounding boxes of the nanite clusters that are using WPO. Remember how WPO makes nanite treat the geometry as dynamic? If a cluster's bounding box expands way too much because of extreme WPO displacement values, it stays visible for longer, which hurts nanite's culling efficiency.
Ah, right. So clamping the maximum displacement helps keep those dynamic bounding boxes tighter, which in turn improves nanite's ability to cull things.
Exactly right. This setting isn't just about visually limiting how much the leaves sway back and forth. It's a direct performance tuning parameter that significantly affects how nanite culls dynamic geometry. It is vital for dense foliage where you might have thousands or millions of clusters potentially being affected by wind calculations. You must set this value reasonably.
Can we still use vertex colors to control the WPO intensity on nanite meshes, like painting branches black and leaves white?
Absolutely, yes. And this is a powerful and very widely used technique for adding artistic control to WPO. Nanite meshes fully support vertex colors. You can paint these colors onto your foliage assets in your DCC software, like Blender, Maya, or ZBrush, or sometimes even directly in the Unreal Engine editor on the mesh asset itself. You then sample these vertex colors in your material's WPO logic to control the intensity of the wind effect per vertex or per area. For instance, just like you said, you can paint the thick, woody base of a branch with black, meaning zero WPO influence, and the thin tips of the leaves with white, meaning full WPO influence, to create a much more natural hierarchical wind effect where the larger, stiffer parts move less and the smaller, lighter parts sway more realistically.
What about subsurface scattering, SSS? That's pretty vital for making leaves look realistic, especially when light shines through them.
Subsurface scattering is definitely vital, for achieving that realistic look where light appears to penetrate the thin leaf material and scatter within it before exiting. It gives leaves that soft, often translucent appearance, especially when they're backlit by the sun. The two-sided foliage shading model in Unreal Engine is often recommended for foliage assets. It provides a good out-of-the-box SSS effect and is specifically designed to handle lighting correctly on thin, two-sided geometry like leaves, making sure both sides get lit properly. You can also implement SSS via custom material logic if you need more control, perhaps using an SSS mask texture packed in your atlas to control exactly where the SSS effect applies, ensuring it's primarily on the thin leaf blades and not on the more opaque woody stems or branches.
Are there any specific material nodes or special tools in Unreal Engine that are designed to work specifically with nanite materials?
Yes, Unreal Engine does provide specific tools for authoring nanite-aware materials, which is helpful. There's the Nanite Path Switch node. This node allows you to define different material logic or different levels of complexity for the nanite rendering pass versus potentially a non-nanite fallback rendering pass if you have one set up. This is useful for optimizing calculations that might only be relevant or performant when running on the nanite rendering path. Even more powerful, perhaps, is the Nanite Override material slot. This is available in the settings for materials and material instances. You can assign a completely separate material asset here. If you do, any nanite-enabled meshes that are using the base material will automatically render using the override material instead whenever nanite is active for rendering them. This offers a really clean and organized way to create entirely separate, potentially much simpler or more optimized material versions specifically for nanite rendering without cluttering up your main material graph with lots of switches.
I also heard about a relatively new way to paint textures or colors directly onto instances in the editor, not just the base asset.
Yes, that's right. Starting in Unreal Engine 5.5, the texture color tool, often referred to as mesh painting in this context, though it's painting vertex colors technically, allows you to paint directly onto both nanite and non-nanite mesh instances right there in the editor viewport. This is a really powerful artistic tool because it lets you add unique color variations, maybe tints, dirt, moss, or other painted details, to individual foliage instances that you've placed in your scene. It helps break up visual repetition in large placements like forests or fields, and adds a lot of visual interest without needing unique textures for every single instance. This functionality requires using specific new mesh paint material nodes within your material graph to actually read and display the painted vertex color data on those instances.
Okay, last question on materials for now. What about virtual texturing, VT? Is that related to nanite foliage? Do we need it?
Virtual texturing, or VT, isn't strictly a nanite feature itself, no, but it is highly recommended and often used alongside nanite assets, especially complex ones. Think of VT as doing for texture data what nanite does for mesh data. It's an efficient system for streaming and rendering very large texture data sets without having to load absolutely everything into GPU memory at once. Using VT can be very helpful for managing the texture memory footprint for the potentially high-resolution textures you'll inevitably be using on your detailed nanite foliage assets, especially if you have many unique texture sets across your environment or very large texture atlases. It complements nanite very well on the data streaming side.
Okay, perfect. Let's pull together the material and texturing side of things then. Atlases are still useful, but they hold PBR maps for your 3D components, plus maybe handy utility maps like ID maps. The single most important performance rule is to prioritize opaque materials. Avoid masks wherever possible because they are significantly more expensive with nanite. WPO for wind is supported but can be costly on dense meshes. It's vital to clamp WPO displacement using that material setting and keep your WPO logic simple. Vertex colors are great for WPO control, letting you mask intensity realistically. The two-sided foliage shading model is helpful for getting good SSS easily. Use nanite material overrides or path switches for targeted optimization. The mesh painting tool adds useful per-instance variation, breaking repetition, and virtual texturing, VT, is recommended alongside nanite for managing texture memory effectively.
Excellent. Now that you've covered the fundamental shifts, the artistic considerations, the core modeling principles, and the critical material setup, let's try and combine all of that knowledge into a comprehensive, step-by-step asset creation workflow. Going from the initial concept and reference gathering right through to getting your finished nanite-ready foliage asset working correctly in the Unreal Engine world.
Okay, sounds good. So step by step, what does that ideal nanite foliage workflow look like?
All right. Step one is always reference gathering and deconstruction. Collect high-quality visual references. Photos are great. Botanical illustrations can be incredibly helpful, maybe even real-world studies if you can get them. And importantly, spend time really analyzing the plant's structure. Its overall silhouette, how the main branches grow and divide, the specific shape and arrangement of the leaves, the typical density and clumping of the foliage mass. Understanding the underlying botany of the plant you're trying to create is absolutely crucial for building a convincing 3D representation that feels right.
Makes sense. Once you understand the plant structure, step two is actually building the geometry.
Yes. Step 2 is base mesh creation and sculpting. For the small elements like leaves, petals, or needles, model them individually with geometric thickness. Remember those techniques like bridging edge loops to create thickness, insetting faces to prepare for surface detail, or using modifiers like solidify and blender are key here. Then you move to your sculpting software like ZBrush to add the fine organic details. For leaves, this means sculpting vein patterns, subtle surface texture, maybe slight folds or imperfections. For branches and stems, you sculpt the bark textures, knots, and natural growth patterns. And make sure you model branches with enough segmentation so they can bend naturally if you plan to use wind animation later, whether WPO or skeletal. For large tree trunks, you can either sculpt them from scratch, which gives you full control, or increasingly commonly, you can start with Scan 3D assets from libraries like Megascans. Just be aware, as we mentioned, that raw scans are often exceptionally dense, sometimes billions of triangles. Even with Nanite, they might need some processing like aggressive decimation or maybe even retopology before importing, just for better editor performance or if you have specific UV or rigging needs. I remember reading one artist mentioning they use LOD3 of a scanned trunk even before enabling Nanite just to make working with it in the editor smoother because the source was so heavy.
Right. Speaking of retopology, is that still a required step with Nanite being so tolerant of density? What's step 3?
Retopology optimization is step 3, and it's definitely conditional now. Nanite is very forgiving of dense, less than perfect topology. So often, a high poly mesh directly decimated from your ZBrush sculpt can be imported and enabled for Nanite without needing a traditional low poly retopology pass at all. However, retopology might still be beneficial or necessary in specific cases. Like if you need a very specific clean topology flow for complex deformation, maybe for precise WPO control, or if you plan to use skeletal rigging for heroic assets, or if the base sculpt is just astronomically dense to the point where it significantly impacts Nanite's internal processing time or the final disk size of your game unacceptably. Or sometimes, simply if having a cleaner mesh makes the UV unwrapping process significantly easier and faster. The goal here isn't necessarily a traditional low poly retopo like we used to do, but rather generating clean, well-behaved geometry where it's needed. Again, critically, avoid exporting heavily faceted geometry on dense meshes that significantly hurts Nanite performance and compression. Smooth those normals.
Got it. Step 4 then must be UV unwrapping and texture baking. Pretty standard stuff, but are there any 9 specific considerations here?
It's standard workflow, yeah, but absolutely crucial for final quality. Step 4, UV unwrapping and texture baking. You need to efficiently unwrap your 3D components. If you're targeting a texture atlas, you lay out your UV shells carefully to maximize space and maintain a consistent texel density across all the different parts of your asset. Then you bake essential maps from your high poly sculpts down to the mesh that you'll actually use in-engine. Common maps include normal map, obviously, ambient occlusion, AO, curvature, maybe a thickness map, which can be useful for controlling SSS intensity later, and critically, an ID map. Remember that ID map? It's big from polygroups, material IDs, or maybe colored vertices in your DCC, and it's extremely useful for easily masking different parts of the asset during the texturing phase later on. When you're baking, use high secondary ray settings for maps like AO, curvature, and thickness for better quality results. And try to work with ACS color space and tone mapping during baking if your project uses ACS, as this helps ensure better consistency between how your textures look in your baking software and how they appear in Unreal Engine.
Okay, let's do another quick check-in. We're walking through the pipeline nicely. Started with reference and deconstruction, then 3D model and sculpt detailed parts, focusing on form and thickness. Decided if retopology is needed, often not strictly, but sometimes. And now we're preparing for textures by unwrapping and baking essential maps, especially making sure to bake ID maps because they're super helpful for texturing.
Exactly. So step 5 is texturing. This is typically done in software like Substance Painter or perhaps Substance Designer. Here, you create your standard PBR maps. Albedo, your base color, roughness, and metallic, which should generally be very low or 0 for most foliage materials. You also create any foliage-specific maps you need, like an SSS intensity or color map, and perhaps an opacity map only if you're using masked materials very sparingly for those hyperfine details we discussed earlier. You can heavily leverage your bake utility maps, the AO, curvature, ID map, to drive procedural effects within your texturing software. This lets you add realistic wear, dirt, subtle color variation, or edge highlights automatically, saving a lot of manual work. And remember, Nanite supports vertex colors, so you can paint these onto your mesh instances in the DCC or in Unreal Engine, and then use them in your material shader to control things like subtle color variance between instances, wind intensity masks for WPO, or maybe even wetness effects.
Now, for complex plants like trees, SpeedTree is often the go-to tool for assembly. How does that fit into a modern Nanite workflow? Is it step 6?
Yes, SpeedTree is invaluable for assembly in SpeedTree, step 6, when it comes to creating complex plants and trees efficiently and realistically. You import your individually modeled and textured 3D components, your detailed leaves, twigs, sections of bark, flowers, fruit, etc., into SpeedTree as mesh assets. Then you use SpeedTree's powerful procedural generation tools to automatically grow, arrange, and distribute these components onto a trunk and branch structure, creating the full tree or plant according to botanical rules and parameters you set. SpeedTree also has very sophisticated built-in tools for creating realistic wind animation, the UT. This is where integrating SpeedTree output with Nanite in Unreal Engine has presented some significant challenges historically. Specifically, it related to how SpeedTree handles UV channels for its wind and internal LOD system.
Right. What was the specific problem there? Why didn't it always work smoothly?
Well, a primary issue reported by many artists was that older versions of SpeedTree, or certain export settings, often utilized more than the 4 primary UV channels that Nanite currently supports for the main mesh data stream. Vertex colors can sometimes act like a 5th channel for data, but the core UVs are limited. This mismatch in UV channels, where SpeedTree might be trying to pack wind data or light mapping UVs into UV5 or UV6, could cause the SpeedTree wind animations to fail completely or behave incorrectly when the asset was imported into Unreal Engine and converted to Nanite using those older workflows. Often, the result was just a static mesh that didn't animate at all.
Okay, so how do you make SpeedTree Wind work reliably with Nanite now? What's the recommended approach?
Artists have reported much better success recently with a specific combination using SpeedTree 10. First, you need to use the game wind type within SpeedTree itself. This wind system is specifically designed for real-time engines. Second, you need to export the asset from SpeedTree in the .st9 file format. This particular combination, game wind and .st9 export, is reported to better preserve the necessary wind animation data in a way that is compatible with Nanite's current UV limitations in Unreal Engine. Exporting with older legacy wind types from SpeedTree often caused the issues. Now, if that specific workflow still presents problems for some reason, there are alternative workarounds people have used. Things like manually modifying the SpeedTree wind material function within Unreal Engine's core SpeedTree master material to try and remap or reinterpret the data to align with Nanite's UV limits. Or employing the Pivot Painter 2.0 workflow, which involves baking animation data into extra UVs and textures using external tools or plugins, but that's a significantly more complex setup. So the key takeaway when exporting from SpeedTree for Nanite is focus on the .st9 format, use the game wind type, make sure you export your high-resolution geometry since Nanite will handle the loading, ensure vertex colors are preserved if you're using them, and be mindful of that 4 UV channel limit for core mesh data. SpeedTree's internal geometric LODs are much less critical now because Nanite will handle the geometry simplification itself.
Gotcha. So once we have the final asset, either from our DCC or from SpeedTree, using that recommended workflow, step 7 must be importing it into Unreal Engine and configuring Nanite properly.
Right. Step 7, import into Unreal Engine and Nanite configuration. You import your FBX file from your DCC, like Blender, Maya, ZBrush, or the .st9 file from SpeedTree. Enabling Nanite itself is really straightforward. You just open the static mesh editor for the imported asset, go to the details panel, find the Nanite settings section, and simply check the Enable Nanite Support checkbox. Then hit Save. That's it for the basic enabling.
And are there specific Nanite settings in that static mesh editor panel that are particularly important for foliage assets? Things we need to tweak?
Absolutely. Besides just checking Enable Nanite Support, the single most crucial setting for Nanite Foliage is Preserve Area. You absolutely, almost universally, want this setting checked for most types of foliage, especially trees and bushes with lots of leaves. Remember why. As Nanite simplifies the geometry at distance, especially aggregate geometry like trees with many separate leaves, it removes small elements. This can make the foliage visually thin out and look wrong. Preserve Area combats this by slightly dilating the open boundary edges of the remaining simplified triangles, effectively scaling them up just a tiny bit to help maintain the perceived density and visual mass of the foliage at distance. It's typically not needed or even desirable for other types of meshes like rocks or buildings, but for foliage, it's vital. Also, remember that max world position offset displacement setting we discussed. While it's technically a material setting, setting it correctly is a critical part of your overall nanite configuration for foliage because it works with Nanite's dynamic cluster management system, so make sure you set that in the material. Other nanite settings in the mesh editor, like position precision, keep triangle percent, which relates to fallback meshes, or explicit tangents. They're generally less foliage specific or usually fine at their default values, but it's always good practice to understand what they do eventually.
Okay, makes sense. Step 8 is finally getting this beautiful nanite-enabled foliage placed into our actual level. How do we do that?
Step 8. Foliage placement and instancing. Once your assets are imported, nanite-enabled, and have the material set up correctly, they are ready for placement in your world. The primary tool for this in Unreal Engine is the Foliage Painter. You access it via the Modes drop-down menu. Select Foliage Mode. This tool allows you to paint instances of your nanite-enabled static meshes directly onto landscapes and other static mesh surfaces in your scene. Under the hood, the Foliage Painter utilizes hierarchical instance static meshes, or HISMs, which are specifically designed for efficiently rendering very large numbers of instances of the same mesh, and they are fully compatible with Nanite. You can also use the landscape grass output system, which is another powerful way to place foliage. This method allows you to procedurally place foliage meshes directly tied to the materials applied to your landscape terrain. You assign your nanite foliage meshes to landscape grass types, which are then configured within your landscape material layers. Many marketplace foliage assets use this system for grass and small plants.
Now, even with Nanite's amazing power, are there still any hard instance limits or traditional culling settings we need to worry about when placing potentially millions of foliage instances?
Yes, even with Nanite, there are still some limits and traditional settings that remain relevant and important to manage. Unreal Engine has a hard limit across the entire scene and all types of instances, not just foliage, of roughly 16 million streamed-in instances visible at any given time. That's a lot, but it's not infinite. And while Nanite provides incredibly powerful automatic view-dependent culling and level of detail based on screen size, traditional foliage placement settings like end cull distance or minimum screen radius are not obsolete. You should still absolutely use these. Think of them as providing coarse, artist-controlled culling. In incredibly dense scenes, these settings provide a broader, earlier filter on which instances Nanite even considers for rendering in the first place. They work in conjunction with Nanite's fine-grained operations, helping you manage that global instance budget and providing an extra layer of optimization, especially for very distant or very small elements that might otherwise still incur some Nanite processing cost.
Right, fantastic. Let's quickly recap this entire comprehensive asset workflow one more time, hitting the key flashcard points. It starts with thorough reference and deconstruction, understand your plant. Then, 3D model and sculpt individual components focusing on form, thickness, and detailed organic surfaces. Smooth normals are critical. Conditional retopology depending on needs, but Nanite is tolerant. UVs and texture baking are standard but vital. Make sure to bake ID maps as they are incredibly useful for texturing later. Texturing uses PBR principles plus foliage-specific maps, leveraging baked data and vertex colors for control. If using SpeedTree for assembly, pay close attention to the SpeedTree.st9 plus GameWin export settings for the best Nanite compatibility right now. In Unreal Engine, import and enable Nanite, and crucially, check preserve area in the static mesh editor. And remember to clamp WPO material using that crucial max displacement setting in your material. Finally, foliage placement using the Foliage Painter grass type tools, being mindful of global instance limits and cull distances as coarse filters.
Perfect summary. So we've now covered how to create the static nanite-enabled foliage assets themselves and get them efficiently placed into the world. Now we get to the really big question for making these incredibly detailed environments feel truly alive. How do we actually bring that geometry to life with dynamic wind animation?
Right, the motion, that's key. We know World Position Offset, WPO, is the standard material-based method, and you also mentioned the potential for using skeletal animation somehow. Let's really deep dive into WPO wind for nanite foliage first. Focus on exactly how it works under the hood, with Nanite, and what the major implications are for performance.
Okay, transitioning into wind animation, as you mentioned, there are two primary methods we'll discuss. World Position Offset, WPO, which is entirely material-based, and rigged skeletal meshes, which can potentially be driven by compute shaders for animation. Let's start with WPO, as it's the much more established technique and the one you, as a developer, are likely already familiar with from traditional foliage workflows.
Okay, so technically, how does WPO actually interact with the Nanite system? What's going on there?
Right. WPO operates entirely within the material's vertex shader stage of the rendering pipeline. It applies mathematical calculations typically driven by things like time, various noise functions like simplex or Perlin noise, maybe control textures, and often vertex colors painted onto the mesh to displace the original position of each vertex in world space. This creates the illusion of movement, like wind blowing through the leaves. Now, when you apply a material using WPO to a nanite mesh, Unreal Engine has to treat that specific piece of nanite geometry as dynamically deforming. It can't assume it's static anymore. To handle this, the nanite system splits the mesh into smaller processing units called clusters, and each cluster needs its own bounding box for culling purposes. Crucially, for WPO-affected clusters, these bounding boxes must be conservative. They have to be calculated to be large enough to encompass the maximum potential displacement that the WPO calculation in your material might cause for any vertex within that cluster over time.
Ah, okay. So if a leaf cluster could potentially sway, say, a foot to the left and a foot to the right due to your WPO function, its nanite bounding box has to be calculated as at least 2 feet wide to cover that full range of motion, even if it's currently only swaying slightly or not at all.
Exactly right. The system has to account for the worst case or maximum possible reach defined by your WPO shader and that max displacement setting. And the culling of these dynamic nanite clusters, figuring out which ones are off-screen or fully occluded by other geometry, then has to happen dynamically on the GPU every single frame. This dynamic treatment inherently prevents Nanite from fully utilizing some of its most powerful optimizations, which rely on being able to analyze and preprocess the geometry statically during import or level load time when it knows the geometry won't move. There's also a subtle technical detail related to tangents. Nanite doesn't store traditional per-vertex tangent vectors from the source mesh in its highly compressed internal format. Tangent space information, which is needed for things like correct normal mapping and lighting calculations, is instead derived mathematically in the pixel shader. With complex WPO that drastically changes the orientation of surfaces or edges between adjacent nanite clusters, this can sometimes lead to subtle visual breaks or lighting artifacts where the derived tangent space doesn't perfectly match the deformed geometry right at those cluster seams. It's usually minor, but something to be aware of with extreme WPO.
Okay, so the bottom line is WPO makes nanite geometry dynamic, forces these conservative, potentially larger bounding boxes, and requires dynamic GPU culling for those parts, which all sounds inherently less efficient than how nanite handles static geometry. Let's really break down the performance implications. What are the specific costs?
Yeah, the performance analysis for using WPO on Nanite Foliage reveals several distinct bottlenecks you need to be aware of. First, there's the raw vertex shader load and material complexity. Remember, the WPO calculation runs for every single vertex that Nanite decides it needs to render for that frame. If you have intricate WPO logic in your material, maybe involving multiple layers of noise functions, numerous texture samples for control masks or variation, or complex mathematical functions that significantly increases the GPU load per vertex. And because Nanite allows for and often results in incredibly high vertex counts on your foliage assets, that per vertex cost is amplified dramatically. As the source documentation explicitly states, when using World Position Offset, WPO, more vertices equal higher cost. Complex WPO logic directly increases the number of shader instructions that must be executed for every visible vertex, potentially millions of times per frame for dense foliage.
And how does this dynamic nature affect nanite's core strength, which is supposed to be efficient culling?
WPO has a significant negative impact on nanite culling efficiency, unfortunately. Those expanded cluster bounding boxes, which are necessary to cover the potential WPO displacement range, mean that nanite clusters remain visible and have to be processed even when a static version of the same geometry with a tighter bounding box would have been culled because it was determined to be off-screen or fully occluded by something closer. This is precisely why clamping the WPO displacement using that max world position offset displacement setting in the material is absolutely crucial for performance. It directly helps maintain tighter bounding boxes for the dynamic nanite clusters, which in turn improves the culling efficiency. Less stuff stays active unnecessarily. Furthermore, remember that foliage is inherently aggregate geometry, lots of small, disconnected parts. This type of geometry already challenges Nanite's simplification and culling algorithms. As we discussed earlier, it's just less efficient with porous structures compared to solid ones, and tends to have a higher triangle count per screen area, naturally leading to more overdraw. WPO can exacerbate these existing aggregate geometry issues and overdraw problems by keeping more clusters active for longer, due to larger bounds, and potentially increasing their perceived screen space complexity as they move around.
But I remember a note you mentioned earlier about the porous nature of foliage, maybe helping with occlusion culling specifically, even with WPO.
Yes, that's a valid nuance mentioned in some technical discussions. The quote was something like, foliage using WPO is less problematic in terms of occlusion because the foliage is filled with holes and cannot really occlude itself. This suggests that WPO's negative impact specifically on occlusion culling, where one object hides another, might be less severe for porous foliage than it would be for, say, a dense, solid wall animated with WPO that could fully occlude large parts of the scene behind it. However, this doesn't negate the other performance issues related to Nanite needing to manage more dynamic clusters with larger bounding boxes, and the general cost associated with rendering many overlapping, potentially moving meshes overdraw. Both of those problems are definitely worsened by WPO, even if the pure occlusion aspect is slightly less of a factor for foliage compared to solid objects.
Okay, so we have high vertex shader cost, especially on dense meshes, and reduced culling efficiency because of the dynamic expanded bounds. What about the interaction with shadowing, specifically with virtual shadow maps, or VSM? You hinted this was a big one.
Yes, this is arguably the most significant performance hit you will typically face when using WPO on Nanite Foliage in Unreal Engine 5. VSM, which is the default high-quality dynamic shadowing system, relies heavily on caching shadow information generated from static geometry to be efficient. WPO's dynamic vertex position changes constantly invalidate the VSM cache for any surface that is using WPO every single frame. This forces frequent, incredibly costly recalculations of the shadow depth information for all those moving surfaces.
Whoa, invalidating the entire shadow cache for moving foliage every single frame. That sounds like an absolute disaster for performance, especially in a dense forest scene.
It really, really can be. Performance profiling in scenes with dense nanite foliage using WPO often shows that the shadow depth rendering pass becomes a major, sometimes the primary, bottleneck. For instance, simply disabling WPO on nanite foliage in a complex scene has been observed to dramatically reduce the shadow depth cost, sometimes dropping from over 20 milliseconds down to just 2 milliseconds or even less. That's a massive order of magnitude performance gain just by stopping that constant WPO-induced VSM cache invalidation. It's a huge deal.
Yikes. Okay, are there ways to mitigate this painful VSM invalidation? Can we lessen the hit somehow?
Unreal Engine does provide some mechanisms to try and help, though their effectiveness can vary depending on the specifics of your scene and setup. There's a console variable, r_shadow.virtual.cache knock material position invalidation range. This tries to limit the VSM invalidation effect to only happen for foliage closer to the camera, potentially reducing the cost of distant foliage WPO invalidating the cache, but its consistent impact is sometimes debated in the community. A much more effective and recommended solution, introduced in Unreal Engine 5.3 and later, is the shadow invalidation type property. This is available on actors, including foliage actors placed via the foliage painter or procedural systems. Setting this property to static for your foliage actors is highly efficient, particularly when you combine it with a WPO disabled distance, which we'll discuss more. What static invalidation does is it allows the WPO calculation in your material to deform the visual geometry so the leaves still move, but it prevents that WPO movement from updating the shadow representation in the VSM cache. This means the shadows cast by the foliage effectively remain static based on the original mesh position, even though the leaves themselves are moving visually. This cleverly avoids the constant cache invalidation and the associated performance cost. Nevertheless, the fundamental combination of VSM plus nanite foliage plus WPO remains a challenging and often expensive configuration unless you manage it very carefully using these available tools.
What about the memory footprint for WPO itself? Does adding wind animation add a lot of extra memory cost?
Not really, no. The WPO calculation logic itself, being part of the material shader, doesn't add significant mesh data memory. The primary memory usage for nanite foliage comes from storing the high-resolution nanite geometry data itself. Of course, if your complex WP logic requires extra textures, like noise textures or control masks, or involves large, complex material function graphs, that will add somewhat to your texture memory usage or your shader cache size. But the core performance problem with WPO isn't usually about its memory footprint. It's about how WPO fundamentally conflicts with Nanite's and VSM's primary optimization strategies, both of which rely heavily on being able to perform static analysis and utilize caching effectively. WPO makes things dynamic, breaking these core assumptions and causing those cascading performance hits throughout the rendering pipeline, especially in the shadow rendering.
Okay. So just to summarize the core WPO challenges for nanite foliage again, because this seems critical. It operates in the vertex shader, making nanite geometry dynamic. This forces larger, conservative cluster bounds and hurts nanite's efficient static culling. It significantly increases vertex shader load, especially on dense meshes. It can exacerbate the inherent overdraw issues with aggregate foliage geometry, and most painfully, it causes constant VSM cache invalidation, making dynamic shadows incredibly expensive.
Exactly. That's a perfect summary of the pain points. Given those significant challenges, optimization is absolutely key if you intend to use WPO on your nanite foliage effectively. So what are some crucial techniques you need to employ?
You mentioned a distance setting earlier. That sounded important.
Yes. The WPO disable distance is probably one of the single most effective optimizations you can implement. You configure your foliage instances in the foliage tool settings or on the HSM component to fade out or completely disable the WPO calculation beyond a certain distance from the camera. This can provide massive FPS gains because it completely eliminates the WPO calculation cost, the need for dynamic bounds, and crucially, the VSM invalidation cost for all that distant geometry where subtle wind motion is likely less noticeable or important anyway. You absolutely should be using this. Unreal Engine 5.1 and later also introduced a console variable R-optimized WPO, enabling this attempts to improve the engine-side handling of WPO calculations, potentially activating them only when truly needed based on visibility, which might offer some benefit. And you can profile if that other console variable, rshadow.virtual.cache.max material position validation range, helps limit distant VSM invalidation in your specific scene, though honestly, the static shadow invalidation type property is often more reliable and easier to control.
And that static shadow invalidation type we just discussed, that sounds like a must-use setting too.
Absolutely crucial. Setting the shadow invalidation type to static on your foliage actors, remember this is available from UE 5.3 onwards, is vital for mitigating that massive VSM cache invalidation performance hit. It allows the visual movement from WPO, but prevents the shadows cast by the foliage from constantly updating based on that WPO, which is a huge performance win, especially when you combine it with a reasonably aggressive WPO disable distance.
And the setting in the material itself, the displacement clamp.
Yes. Using max world position offset displacement in the material editor to clamp WPO is effectively non-negotiable for good performance on dense nanite foliage using wind. It directly helps keep the nanite cluster bounding boxes tighter, which significantly improves culling efficiency, as we discussed. The preserve area setting on the mesh itself is also important here again for maintaining visual density at distance after nanite simplification has happened, regardless of whether WPO is active or not. Additionally, you should always aim for material simplification. Keep your WPO logic in the shader as minimal as possible while still achieving the look you want. Fewer texture samples, simpler mathematical functions, all of this lowers the per vertex cost, which adds up quickly on nanite meshes. And finally, consider selective application. Maybe you only need to apply complex WPO to the most visually impactful foreground elements, or maybe you only apply WPO to a certain percentage of instances using random per instance values from the foliage system to break up the uniformity and save cost.
Okay. Even with all these optimizations applied, are there still fundamental limitations inherent to using WPO on nanite foliage that we just have to live with?
Yes, definitely. Even when you apply every known optimization, certain limitations exist. The aggregate geometry issues persist. Dense forests composed of millions of small, separate geometric leaves with WPO applied will still likely be significantly slower to render than an equivalent triangle count represented by more solid nanite geometry. The challenges for nanite culling and managing overdraw are just inherently exacerbated by the dynamic nature of WPO on this type of geometry. Speed tree wind compatibility remains a known potential pain point. The default or older speed tree wind systems often don't work correctly with nanite WPO due to those UV limitations we talked about. This requires using specific workarounds like modifying the core UE materials, resorting to Pivot Painter, or as we mentioned, using the currently recommended SpeedTree 10.S9 export with game wind combination for the best compatibility. There's also an inherent artistic control versus performance trade-off that you constantly need to balance. Achieving truly realistic, complex, hierarchical wind movement often requires more complex WPO shader logic, which is inherently more expensive to run on high vertex count nanite meshes. You have to find the right balance for your project's needs.
And just to hammer the point home one last time, what about material blend modes, again, in the specific context of WPO performance?
This just reinforces the point from earlier, but it's critical. You should strongly recommend opaque materials for nanite foliage, especially when you are also using WPO. Mask materials are already significantly more expensive with nanite in general, and their performance cost is often exacerbated when combined with WPO due to the processing required for those transparent areas and their negative impact on culling and overdraw calculations. Using full geometric leaves modeled with an opaque material is almost always going to be faster and frankly look better than using alpha mask cards with WPO applied. That note about porous foliage being less problematic specifically for occlusion culling means WPO issues might be slightly less severe in that one specific regard compared to animating solid objects with WPO. But the overdraw and, critically, the VSM invalidation remain major performance concerns that using opaque materials helps significantly mitigate.
Right, fantastic. Let's try to summarize the key performance issues of WPO on nanite foliage and their primary mitigations, maybe like a quick reference table in our minds. Issue 1, VSM cache invalidation, the big one. Mitigations: WPO disabled distance, shadow invalidation type, static, maybe console vars like max material position invalidation range. Issue 2, nanite overdraw reduced culling efficiency pitch mitigations, clamp WPO max displacement setting, WPO disabled distance, preserve area setting on mesh, simplified WPO logic and material. Issue 3, high vertex shader cost ox mitigations, simplified WPO logic, WPO disabled distance, selective application, example only foreground. Issue 4, speed tree wind incompatibility dash mitigations. Modified core UE material, use Pivot Painter 2.0 or a best bet. TOTSI 9 plus gain wind export from speed tree 10. Issue 5, general aggregate geometry rendering cost of mitigations. Use opaque materials, avoids mask cost. Use preserve area setting, except that dense forests are inherently costlier than solid geometry. Okay, so wrapping up WPO, it's the accessible, familiar wind method. Everyone knows how to set it up in the material editor. But it comes with significant performance challenges when used on dense nanite foliage, primarily related to that killer VSM invalidation, reduced culling efficiency due to dynamic bounds, and high vertex shader cost, all of which are amplified by the high geometry density nanite enables. It absolutely requires aggressive optimization and very careful material setup to be viable, especially in large scenes.
Exactly. That's a perfect way to put it. Now, let's explore the alternative path. The more experimental, but potentially more powerful future direction, leveraging nanite's experimental skeletal mesh support with the potential to animate bones via compute shaders directly on the GPU.
Skeletal meshes for plants.
Yep.
Like rigging trees with bones. That sounds like a very different approach indeed.
Yeah.
And you keep saying it's experimental.
Yes, it's a much more advanced technique and currently still an experimental feature within Unreal Engine. It's definitely not the standard way people are animating foliage right now, but it's an area of very active development by Epic. The goal, conceptually, is to potentially combine nanite's incredible geometric efficiency with the structured deformation capabilities of traditional skeletal animation, and ideally offloading the complex bone transformation and skinning calculations entirely from the CPU onto the GPU using compute shaders. Key features that are being worked on or are emerging for nanite skeletal meshes include things like a new skeletal mesh API designed for simpler and more efficient rendering pipelines, the potential for rendering an entire skinned mesh type like all instances of a specific animated tree, in a single draw call, which could be a huge optimization over traditional non-instance skeletal meshes that each cost a draw call. It also includes support for VSM shadowing on skinned nanite meshes, the ability to use separate animation LODs where nanite handles the geometric simplification based on screen size, but the animation complexity, maybe the number of bones being updated or the frequency of updates, can be reduced independently at distance, and crucially, support for instancing with animation banks. This allows many instances to efficiently share animation data and potentially share draw calls, making large numbers of animated instances much more feasible.
You mentioned recent improvements that are making this more viable now.
Yes, significant progress has been made, particularly in recent engine versions. For example, the introduction and refinement of console variables like Arnanicula skin mesh in Unreal Engine 5.5 and later seems to have unlocked substantial performance gains for rendering skin nanite meshes compared to earlier attempts. Demonstrations have shown frame rates increasing dramatically in test scenes, like going from maybe 1530 FPS up to 4560 FPS for scenes with hundreds of skin nanite meshes. This clearly highlights that it's an actively developed area with increasing viability. But it absolutely remains experimental for now. Full feature parity with traditional skeletal meshes, comprehensive documentation across all use cases, and guaranteed stability are not yet there. It's also worth noting that some early iterations of this feature sometimes involve just attaching static nanite meshes to traditional skeletal rigs, like armor pieces on a character, which is technically distinct from rendering fully skinned nanite geometry where every vertex is deformed. Some reported issues people have encountered with skinned nanite, maybe with complex assets like metahumans, might relate to these different implementation details or specific material complexities interacting with the system.
Okay, so the core idea,
Yeah.
you'd actually rig a plant, maybe a tree or a large bush, with a skeleton of bones. And then you'd write compute shaders to run on the GPU to figure out how those bones should move based on wind simulation.
That's the core concept, yes, for achieving highly scalable animation on potentially very large numbers of nanite skeletal mesh instances. Instead of the CPU having to calculate all the bone transforms for every single animated tree in your forest and then send that data over to the GPU for skinning, the aim is to offload that entire process, both the simulation driving the bones and potentially the skinning itself, to the GPU using compute shaders. This becomes particularly attractive when you think about animating really large numbers of instances like a dense forest where maybe even larger branches on big trees or entire smaller plants might be rigged and animated dynamically.
How would that actually work conceptually? GPU-driven bone animation. What does that pipeline look like?
Well, in the traditional approach, the CPU performs calculations every frame to determine the final position and orientation of each bone in a skeleton, creating what are called bone matrices. These matrices are then sent over the bus to the GPU. The vertex shader on the GPU then uses these matrices, along with vertex weighting information and bone indices stored in the mesh data, to deform the mesh vertices in a process called skinning. That's the standard way. In the GPU-driven aim, you would store the necessary bone transform data, like rest poses and maybe hierarchical information, in GPU buffers. Compute shaders, which are essentially general-purpose programs that run massively in parallel on the GPU, could then perform the simulation. They could calculate wind forces based on global parameters or local interactions, determine how joints in the plant skeleton should bend or twist in response, and calculate the final bone orientations, potentially for thousands of instances simultaneously. This updated bone transform data, now living entirely on the GPU, would then be consumed directly by the nanite skeletal mesh system's vertex shader for the final skinning step, deforming the visible vertices.
Okay, that sounds powerful but complex. What are the potential ways you could actually implement this compute shader-driven bone animation for nanite foliage in Unreal Engine today?
This is where it gets quite technical, and honestly, it's much less documented and standardized than setting up WPO. There are a few potential pathways, though. Pathway A would be developing custom compute shaders for bone transforms. This involves writing your own low-level HLSL shaders from scratch. These shaders would need to simulate the wind, apply those forces to a simplified representation of the plant's bone hierarchy, and calculate the final per-instance bone transforms position rotation. The output bone data from your compute shader would then need to be fed into the nanite skeletal mesh system in a format it understands, potentially by writing into the animation banks feature that nanite skeletal meshes use for instancing. This approach requires really deep engine knowledge, significant expertise in GPU programming, HLSL, skeletal animation principles, 3D math, and understanding the specific internal architecture of nanite skeletal meshes, how they handle sections, chunks, bone index limits, skinning influence modes, etc. It's not trivial. Pathway B might involve leveraging Niagara with plugins. We've seen existing third-party plugins like TurboSequence demonstrate the feasibility of doing large-scale GPU-driven instanced skeletal animation by using Niagara systems combined with compute shaders to manage and animate huge crowds of characters, for example. They perform animation updates like joint bending directly on the GPU and can even support advanced features like inverse kinematics, IK, or tracking socket attachments, which are advantages over simpler pre-baked animation methods like VATs. These systems are often optimized for animating tens of thousands of instances efficiently. While Niagara itself can use compute shaders for managing particle attributes, the direct standard integration path for having a custom compute shader drive the nanite skeletal mesh animation banks is not a well-documented or easily accessible feature out of the box. These kinds of plugins often require custom C++ engine modifications or represent significant plugin development effort themselves. The general data flow for this concept, regardless of the exact implementation, would look something like this. You have input data, like global wind parameters from the game world, maybe per instance properties for variation like stiffness or size, the plant's initial rest pose bone transforms, which feeds into your compute shader. The compute shader runs the wind simulation logic, applies forces and rules to the bone hierarchy structure for each instance, and calculates the new bone transforms. The output is then the updated bone transform data stored in GPU buffers in a format that's compatible with the Nanite skeletal mesh system's skinning process. This logic could also potentially be simplified for distant instances using animation LODs, reducing the compute workload per instance based on distance or screen size.
Okay, that sounds significantly more involved than just tweaking a material. What are the potential performance advantages that might justify going through all that complexity compared to just using WPO?
Well, these are largely theoretical or based on early experimental results for nanite skeletal meshes specifically, but they are potentially very compelling reasons to explore this direction. First, there's the potential for significantly better draw call efficiency and instancing. As mentioned, nanite skeletal meshes are designed with the goal of potentially rendering an entire mesh type, like all instances of your hierarchy animated, in a single draw call. If this combines effectively with GPU instancing using animation banks, where many instances share the same draw call but get unique animation data from the bank, you could dramatically reduce the total number of draw calls needed for very dense scenes with animated foliage. Draw calls are often a major bottleneck in traditional rendering, so this could be huge. Second, the primary performance cost shifts from the vertex shader doing WPO on potentially millions of vertices to the GPU compute workload running your wind simulation and the subsequent skinning process. The overall performance would depend heavily on the complexity of your wind simulation compute shader, the number of bones you have per instance, the total number of instances you're trying to animate, and the efficiency of the skinning implementation itself. Nanite skeletal meshes might have different skinning modes, like allowing more bone influences per vertex, which could impact performance. And crucially, perhaps the biggest potential win is the interaction with nanite culling and VSM. This is a key potential benefit over the WPO approach. The hope in theory is that if the base nanite geometry structure of the plant can be treated as largely static by nanite's highly efficient culling system, and only the internal bone structure and the skinning process are changing the final vertex positions, then the base mesh culling could remain much more efficient than with WPO. The vertex positions are deformed by the skinning process after nanite has potentially culled or simplified the base geometry based on its static bounds, rather than WPO unpredictably expanding the nanite cluster bounding boxes before culling. Similarly for VSM, the potential benefit is that shadow cache invalidation might be significantly less severe, or at least more manageable, if the overall bounding box of the instance doesn't change as erratically or as frequently as it does with per-vertex WPO. Maybe you could tie VSM invalidation only to larger, more significant bone movements like a major branch swing, rather than any tiny per-vertex WPO movement causing an invalidation every frame. This could lead to far fewer costly VSM updates. Now, these are definitely theoretical advantages that are being actively explored by Epic and the community, and they need practical confirmation and refinement as the experimental nanite skeletal mesh features mature. But the potential is there.
Okay, right. So just to quickly recap this alternative experimental path, it involves using Nanite's experimental skeletal mesh support, which is improving, enabled by our Nanitella skin mesh in UE 5.5+. The core idea is to rig foliage and aim for GPU-driven bone animation using compute shaders, shifting the calculation load off the CPU. This approach has potential benefits for draw call efficiency via instancing and animation banks. And theoretically, it could lead to better culling VSM interaction compared to WPO because the vertex deformation happens via skinning after base nanite culling, potentially keeping bounds more stable.
Exactly. Now, what about the practical feasibility, the major challenges, and the current limitations of actually trying to implement this rigged nanite skeletal mesh plus compute shader approach for foliage animation today?
Yeah, it sounds incredibly powerful in theory, but it also sounds like it's not something you can just download a plugin for and use easily right now.
Absolutely not. It's definitely an advanced endeavor with significant hurdles currently. The main barrier is simply the experimental nature of both the underlying nanite skeletal mesh features and the process of developing custom compute shader animation pipelines. While features like our Nanitella skin mesh show great promise in UE 5.5+ Subanopa, the overall system is significantly less mature, less documented, and less battle-tested than the WPO workflow. You're working on the bleeding edge. The development complexity is also very, very high. It requires deep technical expertise in GPU programming, writing HLSL shaders, a solid understanding of skeletal animation systems, 3D math, quaternions, matrices, and familiarity with low-level Unreal Engine subsystems. This represents a much, much higher barrier to entry compared to simply setting up a WPO effect in the material editor. Existing plugins like TurboSequence that achieve similar goals highlight this complexity. They are sophisticated pieces of engineering, often requiring C++ API access for optimal performance rather than being simple blueprint-only solutions. The engine's support and APIs are also, by definition, evolving rapidly because the feature is experimental. Relying on these features means that the specific APIs you might need for direct compute shader control of Nanite skeletal mesh animation banks might be limited, undocumented, unstable, or subject to change in future engine versions, potentially breaking your implementation. And there's one notable current limitation of Nanite itself that directly impacts this approach: the general lack of support for traditional vertex painting. As we discussed extensively, vertex colors are commonly used for providing precise animation control in WPO materials, like masking wind intensity per leaf or branch. Since Nanite currently doesn't support traditional vertex painting access in the same way that standard static meshes do, if you needed that level of fine-grained per vertex control for your skeletal animation, perhaps to control bone influence fall-offs dynamically or blend between different animation states per vertex, you'd need to find alternative methods. Maybe storing masks in different UV channels, or relying solely on the bone weighting data provided by the rigging process itself, which might be less flexible.
Okay, so it's a potentially very powerful future direction, but right now it's more in the realm of complex, cutting-edge R&D for studios with strong technical teams, rather than a ready-made solution for widespread foliage animation. Is that fair?
That's a very fair assessment, yes. The future outlook strongly suggests that Nanite skeletal meshes combined with GPU-driven animation via compute shaders represents a highly promising long-term direction for handling complex instance geometry animation at scale in Unreal Engine. It has the potential to overcome the fundamental performance limitations of WPO for wind animation and aligns very well with modern GPU pipelines and parallel processing capabilities. Plugins like TurboSequence serve as important proofs of concept, demonstrating the technical feasibility of doing GPU-driven instance skeletal animation efficiently. But the primary technical challenge right now seems to be the interface. How do you efficiently and robustly feed those per-instance bone transforms, calculated by your custom compute shader, into the Nanite skeletal mesh system's animation banks or rendering pipeline? The specifics of this interface are much less documented and standardized compared to WPO, and likely require significant R&D effort or clearer C+ APIs and examples from Epic as the feature continues to mature.
All right, let's do a mega recap for this whole rigged nanite skeletal meshes and compute shaders section. It's important to understand the potential and the current reality. Key points. This is an experimental feature, significantly boosted by our Nanio skin mesh in UE 5.5 plus Plensen. The core goal is GPU-driven bone animation using compute shaders, shifting heavy calculation off the CPU. Potential benefits include much higher draw call efficiency via instancing animation banks and potentially better culling VSM interaction compared to WPO if implemented correctly. However, the major challenges are the high development complexity required, deep technical expertise needed, and reliance on evolving, potentially undocumented engine APIs. A current notable Nanite limitation is no traditional vertex painting support, which affects how you might mask or control the animation per vertex. It represents a powerful strategic direction for the future, but it's a significant technical undertaking for most teams right now.
Exactly. Now let's try and bring all of this together with a more direct comparative analysis of the different animation methods we've discussed, touch briefly on other relevant techniques, and discuss the overall challenges that remain for animating nanite foliage effectively.
Okay, sounds good. So putting WPO and the rigged nanite skeletal mesh approach directly side by side again, maybe summarizing the key differences.
Right, if we directly compare them based on what we've discussed, thinking about their characteristics. For WPO, its primary performance bottlenecks are the vertex shader load, especially on high poly nanite meshes, and most critically, that constant VSM invalidation. CPU cost is generally minimal. Its impact on nanite culling is generally negative because it requires those expanded bounding boxes. Its impact on VSM shadowing is highly negative due to the constant cache invalidation. Fidelity allows for broad general wind effects, but achieving complex hierarchical motion convincingly is difficult. Implementation complexity is moderate. It's mostly material graph work that many artists are already familiar with. Memory overhead specifically for the WPO itself is usually minimal. Maturity. It's a mature technique for general animation, but its interaction with Nanite and VSM presents significant performance challenges. For rig compute, its primary performance bottlenecks shift to the GPU compute workload, running the wind simulation, and the subsequent skinning process. CPU cost is potentially moderate, maybe for managing instances and dispatching the compute work. Draw calls aim for potentially one per mesh type plus instancing via animation banks, offering potentially high efficiency. Its impact on nanite culling is potentially neutral or even positive. The base culling could be much better if the static bounds are used effectively. Its impact on VSM is potentially less negative than WPO, possibly allowing for more controlled or less frequent updates if implemented smartly. Fidelity is bone-driven, allowing for much more complex, hierarchical, and expressive motion. Implementation complexity as IGH requires deep expertise in GPU programming, rigging, and engine internals. Memory includes storing skeletal data, bone transform buffers, animation bank data, and compute resources. Maturity. It's currently an experimental feature in UE.
Okay, that's a great comparison. So how do you actually choose which method to use in a real project? It sounds like there's definitely no single best answer that fits all situations.
Absolutely not. There is a clear cost-benefit analysis you need to do depending on your specific scenario and project needs. For example, if you're dealing with dense forests, potentially millions of instances, maybe medium visual detail required for the motion, WPO is only really feasible if you apply aggressive optimizations. You absolutely need things like a WPO disabled distance, setting static shadow and validation, keeping the WPO logic extremely simple. Even then, performance will likely suffer significantly as density increases, especially with VSM enabled. Rig compute theoretically scales better for these very high instance counts that need motion if you can manage the compute workload per instance efficiently. But it comes with that very high development cost and the risks associated with using experimental features. Animation LODs, simplifying the animation at distance, are essential here regardless of which method you choose. Now, for hero trees or unique prominent plants, maybe only a few instances, but requiring the highest visual detail and intended for close-ups, WPO can give you detailed motion, but it becomes very expensive for VSM because you're displacing potentially millions of vertices with potentially complex shaders, leading to constant invalidation. Rigged compute, on the other hand, allows for much more sophisticated, physically plausible, bone-driven animation, like detailed branch dynamics reacting to wind gusts. The VSM interaction might be better if the overall instance bounding boxes remain relatively stable, and the higher rigging and development effort might be justified by the asset's importance in the scene. For distant foliage, WPO must be heavily low-D'd. It often needs to be completely disabled or drastically simplified, maybe just a simple sway, far away to save performance. Rig compute also absolutely requires animation LODs here. You'd need to simplify the compute logic significantly or even switch to completely static poses for distant instances to save GPU compute resources. And considering varying hardware targets. Low-end machines will struggle significantly with complex WPO and the resulting VSM invalidation on dense nanite meshes. You'll likely need extreme simplification or just disable WPO entirely on lower specs. A highly optimized rig compute solution might theoretically scale better across different hardware tiers if you can efficiently adjust the complexity or animation LODs based on the GPU's capabilities. But the base cost of even experimental nanite skeletal meshes is still a factor to consider. Very low-end platforms might simply need very, very simple WPO effects or perhaps no dynamic wind animation at all beyond camera-based effects like subtle sway. It's worth noting, as mentioned in some sources, that while WPO can be slow on nanite, examples exist in major productions, like Fortnite, where large numbers of meshes use WPO or VATs for animation. This indicates that with sufficient optimization effort and careful balancing, it is viable in production, even if challenging. And conversely, early nanite skeletal mesh results are showing promising FPS gains, but it's definitely a newer, less proven path for widespread use right now.
You mentioned VATs again, they're vertex animation textures. We haven't talked much about them as the third option. How do they fit into this comparison for nanite foliage animation?
Right, VATs represent a third viable path, particularly for ambient, non-interactive motion. With VATs, you essentially pre-bake complex animation, maybe from a physics simulation in Houdini or a detailed rig in Maya, into textures. These textures store things like vertex positions and maybe normals over time. Then, a relatively simple material samples these textures frame by frame to displace the vertices of a standard static mesh. Their strengths are generally excellent CPU performance and very low draw calls. The animation is entirely driven by the GPU shader on what the engine considers a static mesh, so there's virtually no CPU animation cost, and it instances incredibly well using standard static mesh instancing. They can also capture very complex, pre-baked motion that might be too computationally expensive to simulate in real time using WPO or even a skeletal rig. Their weaknesses include a potentially large memory footprint for the animation textures themselves, especially if you need long or high-resolution animations. This can significantly impact your texture memory budget. They also offer very limited dynamic interaction. The animation is pre-baked, making it very hard for the foliage to react realistically to real-time events like a character brushing past it or a localized explosion. Blending between different VAT animations smoothly can also be complex to set up. And critically, regarding Nanite, VATs can still cause VSM invalidation if the VAT is sampled per frame and causes per vertex movement on a Nanite mesh. It displaces vertices similarly to WPO in that regard, so you might face the same shadow performance issues unless you use mitigations like static shadow invalidation or disabled distances. It also requires setting up a specific baking pipeline, often involving external software like Houdini.
Okay, so VATs are maybe best suited for repetitive ambient wind like large fields of grass swaying uniformly, or maybe the gentle motion of distant trees where interaction isn't expected or needed.
Exactly. That's a perfect summary of their main use case for foliage. Things like ambient, repetitive wind on grass fields, bushes, or distant tree canopies where the lack of real-time interaction is acceptable. The fact that Epic uses VATs extensively for animating trees in Fortnite demonstrates their viability and scalability in large-scale production, particularly when WPO might be too costly due to VSM issues, or a full skeletal setup isn't necessary or scalable enough for the sheer number of instances. VATs scale extremely well for CPU load and draw calls, but they come with those texture memory and flexibility limitations. So this really creates what you might call a scalability dilemma for animating nanite foliage. WPO performance degrades significantly with nanite density and VSM interaction. Rig compute potentially scales better by aligning more closely with nanite strengths and leveraging GP parallelism, but it's complex and experimental. VATs scale extremely well for CPU and draw calls that have significant texture memory and flexibility limits, and can still hurt VSM performance. There is currently no single silver bullet animation solution that works perfectly for all nanite foliage scenarios. Trade-offs always exist, and a hybrid approach, strategically using different techniques for different types of foliage, different distances, or different levels of required interaction, is often going to be the most optimal strategy in a real production environment.
We've mentioned overdraw with aggregate geometry quite a few times now. It sounds like even with nanite handling the raw triangle counts, this is still a fundamental challenge we need to actively manage for dense foliage.
It absolutely is, yes. Even with nanite's incredible power to render geometry, rendering dense foliage, which is inherently aggregate geometry, many small, non-contiguous pieces, like leaves, still presents significant overdraw challenges. Nanite's culling algorithms are generally less effective at eliminating occlusion between many tiny overlapping elements within a dense cluster compared to how well it culls solid objects. So, strategies to actively manage this overdraw are still crucial. Intelligent modeling. As we discussed in the modeling section, design your leaf and branch clusters carefully to minimize unnecessary internal overlap right from the start without making them look unnatural. Artistic density control. Carefully manage the density of your foliage placement when painting or procedurally generating it in the level. Avoid excessive overlap between instances that doesn't actually improve the visual result from the typical gameplay camera angles. More isn't always better if it just creates overdraw. And sometimes, for very dense ground cover like grass or moss, or for distant tree canopies, using slightly larger, more clumped geometric elements instead of trying to render millions and millions of individual tiny blades or leaf can be a necessary optimization if overdraw becomes a major performance bottleneck.
What about other exciting emerging areas that might impact nanite foliage in the future? You mentioned nanite tessellation earlier and the ongoing development of nanite skeletal meshes.
Yes, these are indeed exciting and rapidly evolving areas that point towards the future capabilities for nanite and foliage. Nanite tessellation, which was introduced as experimental in UE 5.3 and is likely still evolving, refers to the dynamic addition of geometric detail derived from displacement maps at runtime, fully leveraging the nanite system. This has the potential to revolutionize how we handle fine surface details on things like tree bark, complex root structures, or intricate ground cover, allowing incredibly high-frequency detail without having to explicitly model or sculpt every tiny bump. It's still experimental, and its performance characteristics and best practices are still being explored, so it's definitely something to monitor closely in upcoming engine releases. Nanite skeletal meshes, as we've discussed, continue to emerge and improve. Support has been extended, including features like instancing and animation banks. While WPO or speed tree lend on static nanite meshes are still the mainstream approaches for animating foliage today, the future could certainly see complex, rigged hero plants or perhaps even larger swaths of dynamically animated foliage, benefiting from the geometric efficiency of nanite skeletal meshes combined with more sophisticated GPU-driven animation techniques. It's perhaps more speculative for widespread foliage use right now, but it's clearly an active area of development at Epic Games.
And finally, just to reiterate, even with geometric constraints being significantly reduced by nanite, shader complexity must still be a major performance consideration, right?
Absolutely, it's crucial not to forget this. While nanite fundamentally shifts the geometric bottleneck, complex shaders remain a critical performance factor, sometimes becoming the new bottleneck. Foliage materials often naturally have high instruction counts due to needing layers for subsurface scattering, SSS, complex wind calculations, especially intricate WPO, potentially detailed color variation logic, and maybe opacity calculations if masked materials are used. You must still actively optimize shader complexity. Use the nanite-specific tools we discussed, like the nanite path switch node or the nanite override material slot, to potentially use simplified material logic specifically on the nanite rendering paths where appropriate. And always use Unreal Engine's built-in profiling tools, the shader complexity view mode in the editor, the GPU visualizer, Shift plus Shift plus high layer, to identify material hotspots in your scene and optimize them aggressively. These emerging features like tessellation and skeletal mesh support, along with ongoing engine and shader optimizations, point to a continued expansion of nanite's capabilities for foliage, promising even more fidelity, more complex dynamics, and potentially more integrated and efficient GPU-side animation solutions in the future.
Fantastic. Okay, let's try to wrap up our overall analysis and look at the other techniques we touched on. Key takeaways here. The WPO versus rig compute comparison highlights the core trade-offs. WPO is accessible, but struggles badly with VSM and nanite culling due to dynamic vertex movement. Rig compute is complex experimental, but offers potential scalability benefits for draw calls, instancing, and potentially better nanite VSM interaction if implemented well. A hybrid approach, strategically using different animation techniques based on the specific scenario, distance, importance, interaction needs, density, is likely the optimal path in most productions. VATs, vertex animation textures, are a viable alternative, great for CPU draw call scaling on ambient, repetitive animation, but they have significant memory flexibility limits and can still cause VSM invalidation on nanite. Overdraw mitigation on aggregate geometry, like dense leaves, remains a critical challenge even with nanite. Use intelligent modeling and careful density control during placement. Nanite tessellation is an exciting experimental feature to watch, with huge potential for surface detail. Nanite skeletal meshes are emerging and improving, potentially key for hero assets or future large-scale animation, but complex currently. And finally, don't forget to optimize shader complexity. It remains a critical performance factor alongside geometric cost.
Yeah, that covers it well. So in conclusion, nanite has truly fundamentally changed how we approach real-time foliage creation in Unreal Engine. It strongly favors moving towards full 3D geometric assets over the old 2D cards, especially when you pair that geometry with opaque materials for optimal performance. Key modeling strategies involve creating detailed individual 3D components with real thickness, leveraging sculpting for organic details, using polygons purposefully, embracing modularity, and understanding the critical importance of smooth normals, and using the preserve area setting correctly.
And on the texturing and material side, atlases are still useful, but now hold maps for those 3D components. Prioritizing opaque materials is basically non-negotiable for good nanite performance. WPO for wind requires very careful management, especially clamping displacement, and strongly considering static VSM invalidation because of its heavy impact on nanite culling and VSM performance. SSS is important for realism, and nanite-specific material tools like overrides can help with optimization.
And understanding nanite's specific handling of aggregate geometry is crucial throughout the process. Intelligent asset construction and careful density management during placement remain vital, even with the immense geometric power nanite offers.
Wind animation stands out as a primary technical challenge in this new nanite world. WPO is accessible, but has those significant performance impacts, especially with VSM and culling. Speed tree integration requires specific, newer workflows, BH9 plus GameWind, to work reliably. Rigged skeletal meshes animated via compute shaders are still experimental, but represent a very promising, potentially more scalable direction for the future, though they are complex to implement today. And VATs remain a viable alternative for specific ambient animation use cases.
The future is undoubtedly bright, though. Nanite tessellation, enhanced skeletal mesh support, and further advancements in GPU-driven systems are all evolving rapidly, promising even greater fidelity, more complex dynamics, and potentially more integrated and efficient animation solutions down the road.
Absolutely. Success in this new era of nanite foliage really requires adapting your workflows, being willing to experiment with these new techniques, and maintaining a commitment to continuous learning as these powerful technologies continue to mature and evolve.
So we've navigated the complexities of nanite foliage, hopefully, from its core geometric revolution, right through to the tricky nuances of bringing it all to life with believable wind animation.
Yeah, and I think the key takeaway for you, the game developer listening in and maybe trying to wrap your head around all this, is that while nanite offers incredible power and lifts many of those traditional geometric burdens we've struggled with for years, it also significantly shifts where the technical challenges lie. It requires new ways of thinking about art creation, material setup, and especially performance optimization. It's not just about raw triangle count anymore. It's much more about how you build your geometry to work with nanite strengths, how you write your shaders to be efficient in this new virtualized world, and how you handle dynamic motion in a way that doesn't fundamentally fight against the underlying systems like VSM caching.
Exactly. So here's something for you to mull over after this deep dive, a question to take away. Given the trade-offs we discussed for wind animation, the accessibility but potentially high performance cost of WPO, the complexity but potential scalability of rigged skeletal meshes via compute, and the niche utility but memory cost of VATs for the next large natural environment you find yourself working on, where would you strategically deploy each of these techniques? And based on that scene's specific requirements, like density, interaction needs, target platform, which specific optimization or setup step, perhaps focusing first on implementing aggressive WPO disabled distances, or ensuring you have static shadow and validation correctly configured, or mastering that specific SpeedTree.st9 export workflow, which one would you prioritize implementing and profiling first to try and maximize your performance with nanite foliage?